So welcome to CS235. Anyone want to fill it in for us? No? Okay. Oh, you don't even know what class you're in. See, this is why I'm doing it every week, because clearly you don't know what class you're in. So this is lecture 9, and today we're going to be talking about springs. And we're going to be starting basically what are DC motors and how do we use them. It'll be a little bit more of a nebulous lecture than typically. But there are a lot of chicken and egg problems in terms of which came first, the motor or the voltage that controlled the motor or the DAT card that read the voltage, etc., etc. A few administrative things really quickly. We'll be having office hours, or Rob, more correctly, will be having office hours tonight in Clark E110, 7 to 9 p.m. We can't start Lab 2 in terms of actually building the nuts and bolts because we're still laser cutting the parts, because we had a second laser cutter go down. So as we speak, some gentlemen in Hayward are laser cutting the parts, so you don't have anything to assemble yet. So good news is you have your work delayed. The bad news is that I gave you some more quite unintentionally, but it's actually a terrific learning lesson. So remember I asked early in the quarter what the diameter of a half-inch dowel was? Well, I'm going to ask it again. So someone tell me the diameter of a half-inch dowel. There's a tolerance. So the answer is we need to measure it. So what happened... Someone is submitting their homework as we speak. What happened was I made the drawings that I sent out to you and you guys copied for Lab 2 based on MDF that I bought at Osh, and its thickness was 12.7 millimeters, and that was great because that actually is a half inch, and I mean it was off by 1 or 2 thou, but it's not a big deal for wood. But I only bought 3 boards, so I said, okay, great, I'll go back to Osh. And typically, I've never had any problems with MDF not being the dimension it's supposed to be. But I bought 20 of them, and they were all 12.15 millimeters, plus or minus 0.02. So this is why you measure your material before you start designing it for laser cut wood. Because you remember we have these little things here, and then this fits into another plate, and that plate, if built for 12.7 millimeters, but this board here is 12.15, it won't fit right, and your assembly will fall to pieces. So this is very irritating because it means you guys have to modify your CAD. I'm extending the deadline for CAD to Wednesday at class. The good news is, however, that this is, I mean, if this never happens to you again, I'll buy a hat and I'll eat it, because this happens just about every other time that I do something with a new material or a new vendor. I'm actually pretty surprised about this. This is the first time I had issues with MDF. So the new magic number is 12.15 millimeters. I'm not issuing new drawings, because as I was redoing my drawings, I thought, hey, this is such a good lesson. So basically, take your CAD, change the thickness of all the plates to 12.15, and then make it fit. So the overall dimensions stay the same. So if we look at these 2 plates here, and then we have the wheels in between, so that inside dimension stays the same, and all the dimensions between the holes stay the same. Basically, the only things that are changing is how these fingers are fitting together. So it's actually not that bad.
So the only thing that should move, I guess, if you want to fix the inner plate, and then you just move the little T part in that section.
Yeah. So you just shift it over here, like that.
So how do you handle the? First, how did you measure the tolerance here?
I just measured a bunch of boards, and they were off by.
You measure like along the board?
Oh yeah, I just measured a bunch of different. I mean, measuring wood is totally imprecise because it's so soft that as soon as you touch it with the steel calipers, you're squishing it, and then your measurement is wrong. But I, measured along the board and got sort of a running average.
Sorry.
Go ahead.
Well, for this tolerance, should you compensate for that for the 12-tone?
No, just do 12.15 and ignore the tolerance.
So the 30-tooth wheel that we're also making out of MDF is also going to be, are we keeping that at 12?
All of the MDF is now 12.15 millimeters.
Okay. Will that change some of the distance between the plates?
Yep.
Okay.
So, you know, I don't know if you guys noticed, I think the way I set it up was if this is your rollerblade wheel and then this is the 60 tooth, I believe I set it up so that the flange edge of the 30 tooth lines up right here. So it should still line up.
Yeah. Okay.
Actually, the wheel assembly, I was really confused about that. You have a flange bearing and a skate bearing. So is the skate bearing like completely in contact with the flange bearing on the other side?
No. So you know how there are two pockets in the rollerblade wheel?
Yeah.
Both of the bottoms bottom out. Well, the skate bearing without the flange bottoms out on the bottom of the hole, and then the flange is located against the roller plate by the flange.
Yeah.
But they don't touch internally.
But, so it won't slide in by mistake? Because...
So the flange can't slide in because it's got the flange, and then the skate bearing can't slide in because it's against the seat of it. So if we zoom in here, there's a hole here, and that's where the bearing sits right there.
And then is there a washer between the bearing and the spacer? Because you put a spacer in there, right? Yeah.
MBF spacer, no. It is basically a giant shim.
Okay.
So the little annulus that sits in here is just a big shim, basically for assemblability issues. And when you guys assemble it, it will be a pain in the ass, and you'll understand why I decided to give you one giant shim instead of like 30, because you cannot put a stack of shims in there that way.
I have two questions. So my first question is, how thick exactly is that MDF spacer? Is it the same thing?
It's the same.
So
Yep.
it's all the same?
So even that's going to reduce now, right?
Yep. Any part that's MDF is now 12.15 millimeters.
Yeah, because when I was looking at the photo of this, or like the PNG file of the assembly, you had like the spacer kind of stuck out a little bit.
That's because the spacer is touching the flange, but the 60 tooth gear is not. It's not. It's touching the flange, but it's not on the top. So if we zoom in, we have this is the 60 tooth here, and then this is the flange here, and this fits inside, and then the spacer, which is the same thickness, is there. So see that distance here? What's the width of that distance? It's the thickness of the flange. So this 60 wheel and the flange here are at the exact same height, but the spacer is on top of the flange, so that's why it's sticking out a little bit.
But the other side does not have a flange.
Exactly. So the two sides of the wheel look different. One side is flangeless, and it's perfectly easy to assemble stacks of shims there, and that's fine. And the reason I'm using this one is because imagine the last part you're sticking in before you stick the shaft through the rest is like 20 of these little shims. It's impossible to get them to line up in here. So you use one shim here, and then the rest you can see them, so you can line them up.
But then there's no flange there, that's what I'm saying.
There's no flange
On
here.
the other side, so basically the wheel assembly,
Yep.
you have this, if you look, say you're looking at the right one,
Here, let me pull up the assembly, and then we can talk about that more.
My other question is, how do you make parts that are part of two different sub-assemblies?
Say it one last time.
How do you make, like, for inserting one of the shafts, right? How do you make, like, sub-assemblies to external parts?
Sub-assemblies to external parts. I don't...
Parts of a sub-assembly.
Can you give me an example?
Like, so for mine, it was like the screws screwing in down to the shaft. I couldn't really make that screw.
You can.
So I wasn't sure how to do it, because the screw was part of one assembly and the shaft was part of an external assembly.
Oh, I see what you're saying.
Yeah. Like, you can't
yeah.
the screws move down.
Give me 1 sec to pull this up. So the trick for that is, you're correct, you cannot mate them. So what you do is, in the subassembly that contains the screw, you'll put that at the proper height, such that once assembled with the shaft, it is correctly...
So then just do an offset mate.
Yeah.
You can also float the part of the subassembly. So if you look at the little thing on the side
Yeah.
that has the green box, if you click on properties and float it, then all the parts that float in the subassembly will float in the assembly.
Okay, so we're not going to spend too much time on this. I'm happy to talk about these during office hours a little bit more, but there seems to be a little bit of confusion on this, so we'll cover this quickly. Okay, so this is the roll blade wheel assembly, and on this side we have the flanged bearing, and on this side we don't. So let's open up this wheel real quick. You see this little lip here? That's the lip that the unflanged bearing is sitting against. And then on the other side, it's not sitting against that, it's sitting against this right here. So now going back to this assembly, here, just in terms of assemblability, it's not inside of like a hole or anything, so we can use stacks of shims just fine. And then,
Wait, so the flange bearing's actually on the side of the...
see this right here? That's the flange. So the flange is on the side of the 60-tooth wheel. Anyone know why I have that flange there? Because that's what's locating this gear. This gear cannot be concentric with the wheel unless we have some feature to press it onto. Screws are not sufficiently accurate. And even if they were accurate, I mean, look at these wedge type holes. These wedge type holes, the hole's way small. The screw could go anywhere in the wedge, right? So the only thing that is locating this blue hole right here is the flange of the bearing. And you know, it's a precise flange, so it's fine. So that's why I have one flanged and one unflanged. There's no reason to use an unflanged on the other side because I'm not locating anything based on it. The only reason I'm using flanged over here is because, let me see if I can turn this transparent. Hey, there we go. See that? See how that flange is locating that hole inside? Everyone get why I'm doing that?
The other side it's unflanged. It looks like
Unflanged.
Yeah, that's why.
This right here?
yeah. It's flanged.
Nope.
Oh no, just offset it.
No. It's just in the outer race. The reason, anyone know what this here is? That little, that's like the no-fly zone or the DMZ. This is the inner race, this is the outer race, and in between it's recessed just a tiny bit. And it's important to know where it's recessed because why? Anyone know why?
Don't want to impede the ball bearings.
You need to know how to size your shim so you don't touch the ball bearings. So let's go back here and see if that makes sense. Okay, so it's sticking out a little bit, but that's not a flange. If I turn this transparent, you see, there's no flange. And by the way, I didn't make these numbers up. I took the roll blade. I took like 10 of the roll blades and measured them with calipers. So I'm confident in their geometry. All right. Any more questions about flanged versus unflanged on this assembly?
For the bearings, could we take them off your IGS file? Because I have that cut off.
Just take it from the lab 1, and then save a copy, and then take the flange off. Yeah.
And the number of shims on this end depends on how you want to space it, right? Because I have to change it accordingly.
On
In
how
the
you
final
want to
assembly,
space
like,
it.
just basically fitting it. Because you didn't mention the number of shims. I just
Exactly. Yeah, however many shims you need to space it. If you happen to be off by 0.1 millimeters, I really don't care. You just, if you're off by a number in terms of, oh crap, I have 0.4 millimeters left and I only have 0.5 shims, well, that's actually not exactly true. I stock 0.1, 0.2, and 0.5. So if you're off by 0.1, then that means I'm hinting at you to ask me for something else when you're assembling it. I'm hoping you'll ask me for it instead of putting another 0.5 and then you're over constrained.
So today we can only do the nuts and bolts. We can't do any of the building.
We're not going to work on Lab 2 today in office hours because it's better to do it as sort of a contiguous process. If you have SolidWorks issues, then Rob can look at those, and that's for Lab 2. And then if you are one of the unlucky people who didn't get to finish Lab 1 due to me not getting you parts or quals or what have you, then you're welcome to come and work on Lab 1. But I don't have your demo and parts yet. Those are being cut as we speak. Or I dropped them off. They might be drinking Thai iced tea and not doing it. Hopefully they're doing it.
So when is the first day for working on Lab 2?
Whenever they give me the parts. It's been a hell of a process getting them to cut them. So I'm hoping Wednesday. I'm pressuring him quite a bit to get them on Wednesday, but I'll push back the due date, by however many days we were delayed.
What parts were you referring to?
All of the parts for Lab 2. So a second laser cutter went down, so now I'm just shopping them out to a local place, and they're just going to cut all of the parts based on my design. I would like to cut your guys' individual parts to let you see, hey, I took this from design to finished product, but I can't because I don't have a laser cutter. So, okay, let us head on. And so, office hours tonight, 7 to 9 with Rob. Rob does have to leave at 9 precisely, so don't show up late and expect to do stuff. So part of this class, or let me back up. A topic like controls or linear algebra, they're very nice from a lecturing standpoint. A, because you don't have to jug a metric ton of crap upstairs every week. And B, because it's fairly logical what the next topic is going to be. Mechanical design seems a little bit splintered. It's not because I'm schizophrenic, it's because there are just lots of little tricks and tips and widgets, and you sort of design often is a lookup table of what you have to know how to do. Rob, can you zoom in on this, please? So, every now and then, such as now, I will introduce something that we'll discuss for 5 minutes, and then I'll never mention it again. That's just the way mechanical design is, and there's really no way to design lectures around that. So you've seen this all, and you're making basically just the wrist part of this for Lab 2. And I'm just going to backdrive this, and I want you guys to tell me something obvious. Okay, that's good. Huh? It's continuously rotatable. The wires would curl up, and who knows, maybe these wires are severed because I did this and then I kept rotating. So the problem is, continuously rotatable is great, because imagine that I have a gripper here, and Rob, do we get that on tape? Okay, I have a gripper here, and by the way, this is why you don't want wires near a friction drive. Say I wanted my gripper to turn a doorknob, and I don't know ahead of time what type of doorknob it's going to be. Maybe the angle's 90, maybe it's 180, maybe it's some kooky weird thing I designed in my house and it's like a 10-turn doorknob to get it to open. Maybe instead of doing, when humans use a screwdriver, you kind of do this. Maybe I don't want to do that. Maybe I want to grip the screwdriver with my robot arm, and then I just want to spin the entire gripper, right? This is way simpler. If I had, a power supply, it'd be way simpler to grip the screwdriver, not change the grip, and then just rotate that screwdriver until the screw's out, right? Instead of letting go and re-grasping and letting go and re-grasping. So sometimes you need continuous rotation. As another example, and Rob, please zoom in on this. This is one of the omnidirectional wheels I designed, I guess it was my first project at Stanford. This was proof of concept for the PR1, and then later Willow used this as a starting point for the OmniBase that's now on their PR2s. And so the way this works is basically there's a bolt grid here, and that bolts to your base, and then this is able to just keep rotating and rotating and rotating and rotating, because you never know, based on, I don't know, maybe you're in search of the research minotaur and you're going in a labyrinth and crooks and crannies, and you don't know how many times you're going to need to spin the wheel, and you don't want to have to keep track, and right as you're about to break all of your wires, you have to whip back around and start again. So it's much more convenient to have it continuously rotatable. But again, we have all these wires coming off. So does anyone know what the solution to this is? Okay, so we'll start out with just the dumb example. What is this? What type of jack? Okay, and tell me something else obvious about it. Yes, it's a male jack. Yep, it says it's got multiple channels. And then I've got the little one. And so let's look at how this works. Rob, can I get you to come over here for a sec, please? Or someone? Okay. Okay, go ahead. Okay. So you see these two? So we plug them in, and then I can keep rotating this continuously. Hey, look at that. So I'm passing, electrical signals through here, and I'm rotating infinitely. This is the poor man's way of getting continuous rotation with electrical signals routed through it. Okay, I'm good with that. Thank you. The nice version of this, or rather the more abstract term for this, is a slip ring. The poor man's version of this is just an audio jack, and you can get audio jacks that have a lot more channels than your standard audio ones or headphone ones. So for my senior design project at Hopkins, I had we're building a paintball gun turret for an unmanned helicopter, and the slip ring for the turret was an audio jack. I think it had like 6 or 8 channels or something, and it's great because it costs like $2. Does anyone know what a problem with a slip ring like that is? No, you can, depending on the size, you can get pretty high current. The problem is noise. You're scraping metal against metal, and you actually have this weird capacitive noise that it generates through that scraping process. And so for some, if you're driving a motor, it doesn't matter at all, right? But if you had some very low power, weak little signals for sensors, then that capacitive noise you're generating through that scraping process might kill your sensor data. So this is a nice slip ring, and this is actually what's in those omnidirectional wheels that I built. And just to show you real quick, I can rotate this. So this, you see the little sort of lighter gray peg? The lighter gray at the top next to the wires? That's what's rotating, okay? And so I can keep rotating this over and over and over, and you can see that there are quite a few wires coming off of this. So these are sold by Moog, M-O-O-G. And hey, that's like modern art. There's a shadow of someone's soul. So basically, the way this works is you grab the big part, the other thing that's rotating grabs the little part, and then you're done. And a really simple way, you can't see it, I'm not even going to bother doing that, but all I did here, if we were to draw it out, so typically the way they'll work is they'll have a flange, and then this will be the big fat part with all the wires coming off of it. And then there'll be, if we look from above, we'll have a bolt pattern. So we bolt this to a plate, but then you've got this little part, and this is free to spin. We have wires here. You don't have to grab this very hard, just enough to basically overcome the friction between the two. So I actually took a piece of really loose PVC tubing and drilled a hole in it, and then I think I clamped it to the other non-rotating side, and that was good enough. So the nice thing about slip rings is you don't have to hold them really precisely. As long as they're able to rotate, then you're fine. And it's fine if what's holding it is compliant or has backlash. It really doesn't matter because it's not sensing anything, right? It's not like an optical encoder. All you're doing is fixing both sides. And now what's happening inside of here that makes these so much nicer than audio jacks is a lot of R&D and manufacturing for basically how they have these rotating contacts. So depending on the slip rings you get and the quality, some of them might have liquid metal inside of them. Some of them might have little spring-loaded fingers. And also, that audio jack was pretty big, even though it only had 3 channels. I think the little ones I got for these wheels were like 24 channel for that size, which is, that little slip ring was smaller. Let me put it back on the camera. This little slip ring overall is actually smaller than the audio jack and has see, the audio jack's bigger and the slip ring has, I think, 24 channels versus 3. They were pretty pricey. You might get them for $200. That's not really pricey for a robot, but for your guys' final project, that'd be pretty expensive.
So this has to be centered to whatever you're rotating, right?
Not really. It should be, but it doesn't have to be.
But if it's not, then, well, it...
As long as you're not applying high loads here, it doesn't really matter what you're doing. As long as you sort of fix this end and sort of fix this end, it could even be slightly eccentric from the central hole and it will still work. Again, this is not like a mechanical transmission or sensing rotation that has to be real precise. All it has to do is basically the friction between the 2 parts slipping on each other has to be a lot less than ripping and winding the wires. And as it takes a really high load to rip and wind wires, you can do some pretty wacky things with slip rings and they'll actually still perform pretty well. Everybody comfortable with the idea of a slip ring?
Is there anything in between the $200 and the $3 range?
I haven't found anything. I have not. You could even build your own homebrew one where you have, say you took a wheel and I made each one of these thick lines a separate conductive little annulus, and then if we look from above, I could have little, spring-loaded pieces of wire that would be on top of them. It just basically needs to be able to continuously rotate, and the spring loading is a good way of doing that. But they're either total hacks where they were never meant to be used as such, but they're fine. They're homebrew hacks, which might even be worse, and then there's the $200 version. Slip rings are pretty nice little gadgets, and not that many people use them. By the time that you're building 4 of these, it's sort of lost in the cost of screws at the end. Okay, everybody good on slip rings? Any more questions on them? They're very useful. They're sort of a niche thing, but I'm guessing some of you will end up using them. So let's talk about how to use DC brushed motors. So another lecture, we're going to talk about all the others like ultrasonic and servo and stepper and brushless, etc., etc. But sort of the workhorse of robotics is a DC brushed motor. And I'm happy to have discussions with you about the relative disadvantages or advantages of hydraulic and pneumatic, etc., piezoelectric. But for now, basically everyone just uses these. They work really well. We have excellent, electrical models of them. And so this is where the chicken and the egg issue begins, in terms of what are we going to talk about first. So getting a DC brushed motor to move in a controlled fashion is actually quite a bit of work. So I'm just going to sort of start where I think it makes sense, and we'll see how far we get. Okay, so a couple just quick terms. Does everyone know what I mean by feedback and feed forward? No? Okay, that's good. So in controls, there are the terms feedback and feed forward. In feedback, say we took our motor and we'll draw a little marker on it. That's the arrow. And we tell it we want to go right here, okay, to theta. And if this were a stepper motor, we can command the number of steps we toggle a line and it goes tick, 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 tick till it gets to theta. And as long as, say we don't even have anything attached to the motor, it's just the motor just sitting there being pretty and tick, 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 and we're there. We don't have to wonder whether or not we got there. We got there. There was no way we didn't, because we didn't have any loads that would keep the motor from moving. And we know the precise step size of a stepper motor, so that would be an example of feed forward. We didn't have to sense, we didn't have to check at the end whether or not anything had disturbed our motor. Now if this is a DC motor instead of a stepper, if we apply a voltage, it's just going to start spinning like crazy. Okay? So if we think we're going to be smart and somehow apply an electrical signal that's going to tell it to go to theta, we're fooling ourselves, because it's just going to start spinning uncontrollably. And we basically need to put a sensor on here that we're going to feed back around to tell us how close we are. And then all of you I'm sure all of you are familiar with this. Basically, we're going to take a command signal or reference. We're going to put it through our motor plant, through some amplifiers, yada, yada, yada. This is our encoder. This is basically we're measuring where theta is. We feed it back, we subtract it. I'm not going into this today. I know all of you have at least seen this. Is there anyone here who hasn't seen this type of thing? There's no one willing to raise their hand, so I'll assume for now you've all seen it. You can all imagine, though, if you just imagine a dental drill, right? And you wanted to tell a dental drill to go to this position. It's not going to happen. You hit the juice, it starts spinning, and it's not going to stop unless you have some way of sensing it and then adjusting the control of it. So basically, the difference between feedback and feed forward is feed forward will simply go without any measuring and then modifying of the electrical signal you're giving it, and feedback requires you to measure what we just did and then modify the electrical signal that we were giving it. So if we originally told it 5 volts and then we measured and we weren't there, maybe we'll tell it 4 volts next, maybe we'll tell it 6 volts. And again, I'll be much more precise about this in a future lecture. Yes?
So is feed forward the same as open loop?
Yeah, you could think about that, yeah.
And feedback is closed loop control.
Mm-hmm. Yeah, so thank you. Feed forward could be considered open loop, and then feedback could be considered closed loop. You're closing the loop with the sensing. Those terms are correct, Rob. I didn't just commit a cardinal sin of controls or anything. I think they are.
So how do you actually stop that motor? Do you have you just take the current off or you ramp the current down? Or?
We're going to talk about that. This subject is deep and wide and multifaceted, and if I get out of sync in terms of what we talk about when, you're all going to be massively confused and pissed off. So we'll talk about how to draw this block diagram and how do you actually code, say, a PID controller, but we have to do that later. For now, basically, we're going to take an electrical signal, in this case voltage, we're going to hook it up to our motor leads. If it's a stepper motor, it's just going to do 1 tick, and then a second tick, and then a third tick. And the only thing we ever tell it to do is just take another step. So it's feed forward because it always takes exactly 1 step. You don't need to count. But you can imagine a DC motor is like a stepper motor, only it's a random number of ticks every time. So we tell it take a tick and it goes like 10 billion. And you're like, well shit, I only wanted 1 tick. So now I need to measure how many ticks it actually took and then go back and modify the original electrical signal. Okay, great. So let's just start out for revolute joints, so just rotating. We need to sense that position theta for feedback. So we want DC brush motors and they require feedback. So the way we do this, there are 2 basic types of signal. So we have analog and digital forms of measuring the angle. So let's start off with analog. Does anyone know a good analog way of measuring rotation? Potentiometer. Great. I just so happen to have brought said potentiometer. And I'm going to take off the little knob so it looks more like it should. So this is a little fidgets potentiometer, which means that they took a potentiometer and soldered it to a board labeled fidgets. It's really, really simple. It's just a knob, and then there are 3 wires coming off of it. Does anyone know electrically how a potentiometer works? It's a voltage divider. So basically, this will be like 5 volts, and this is ground. And then we'll measure the voltage here. And so this is a giant resistor, but we're actually breaking that off, and this is R1 and this is R2. And as we're mechanically moving where this little arrow is, so if we're at this end, it's like resistor 1 doesn't even exist, and if we're at this end, it's like resistor 2 doesn't even exist. But then in the middle, they're equal. Okay, and by measuring this voltage change is linear with basically the spatial movement that we took, and so we can back out where we are. So let's call this Vn, and then and then we'll call that. How about sig? Yeah, there you go. The signal. So V sig is R2 over R1 plus R2 times Vn. And as we're moving this, the resistors are changing. So basically, as we're rotating, the resistors are changing, and it's linear. So if we draw the curve, this is V sig, and this is theta. It's linear. So this is great. Everybody see how that works? I'm not going through Kirchhoff's current law and deriving it. You can Wikipedia it and see that.
So if the resistor is really big, why do you need a ground? Then doesn't need to be grounded, or? I mean, the resistor is like crazy, right? Why do you need a ground when the resistor actually?
We're putting. Typically, measuring resistance isn't good. We want to measure voltage instead. So we need a power and a ground.
So the current always goes to it?
Mm-hmm. Yeah.
The current always goes to the ground.
Yeah. And this, I hear murmuring. Any problems? Nope. Okay. So that's how a potentiometer works. And again, you can Wikipedia if you want to see how to drive that. And they have rotary and they have linear versions. And they work identically the same way. So just to show you what it looks like on the linear version, these are also called slider pots. See this? And then I'm able to move this. And literally what's happening is this third thing is called the wiper. The little arrow that moves along between both sides of that giant resistor is called the wiper. And so this is the easiest way to see it. You can imagine one end of this slider is ground and the other is 5 volts, and in between is this wiper, so we're measuring the voltage on that wiper. And these actually, if you want to know where to buy these, other than fidgets, if you want different resistances and different geometries, welcome to Sony Digital Handy. Thanks, Sony. They're not a sponsor, by the way. These are sold a lot in audio, and they're called either taper pots or fader pots. And you can get them on DigiKey. You can also get them at Fry's. And they're really terrific because they're super cheap. They're like $2. And the audio ones are actually really high precision and repeatability. So let's discuss a few terms. On this curve here, and actually let me draw it a little bigger. Okay. So this is the ideal curve we'd like, right? It's perfectly linear. But say we have something like this instead. So this would be a problem with what? Linearity. So one potential problem on a sensor like this would be linearity. The other would be is if every time we do it, we have a slightly different curve. So we sort of have a family of curves. You can see there's a region where we could be in here, but it's not the same each time. You could either call that repeatability, and sometimes they'll call that hysteresis. Hysteresis, that might be an I. I don't remember. Yeah, it's an E. Be careful with the word hysteresis. It means it's an overloaded term. It means many different things to many different people and many different topics. I think in this case, repeatability is the same as hysteresis, but you want to, when you're speccing something like this, you want to call the company or a company that makes something like this, and you want to say, hey, what do you mean by hysteresis? And they'll say, oh, let's talk about repeatability, or maybe they won't. Maybe they'll make up some bullshit, and then it's good that you learn that because now you know what it means. And I've basically every time I order a new I/O board or sensor, I call the company and harass them, and it saved me a lot of problems. Okay, so we could use a potentiometer. What's another analog thing that we could use?
Hall sensor.
A what?
Hall sensor.
Yes, a Hall sensor. So let's, under here, we've got potentiometer. And we also have a Hall effect sensor. Anyone know what physical quantity we're measuring with Hall effect sensors? This is magnetic. Okay, so there are many different flavors of these. I'm just going to show you what one of them looks like. So this is pretty small, and I'll put it next to the potentiometer to show you. Everybody see this? I believe this is called an MAE3. This is by US Digital. So basically what it is just a piece of brass that's been machined so that I can locate off of the outside and use the flange to stop it. And it's got a little electrical connector on the back, and I don't think you can see in here, but in the abyss that in the camera looks like an abyss is the center of the universe. And it's also just a tiny little IC chip that's measuring the magnetic flux of a magnet. And so the way this works is, so this is our little housing, the little brass housing that you just saw. And then here's our little IC here. And then if you have a shaft you wish to measure the angle of, this is the shaft, and then they've got these little plugs, and this is a magnet right here. So this is the shaft, this is the magnet, and then this is the sensor. The magnet is round, yes. You don't just use any magnet. You take the magnet that they provided. I don't have any of them, but the way this works is you say, okay, the shaft that I need to measure is 3 millimeter bore. And then you look up A, will it fit, right? You can see if I tried a 2-foot bore shaft, they wouldn't have something because it's bigger than the sensor. So A, you check if they have a bore size that matches your shaft in terms of the magnet, then you order it. And you have to use their magnet, and you have to install it in precisely the way they want it. This distance here really matters. If you screw that up, it won't work. And so this gives us the exact same type of curve over here, which is a roughly linear variability between the voltage coming off of it and theta. And again, you'll give it a power ground, and you'll read out a voltage signal. And again, it suffers from linearity issues. I think these might be like 2.5 or 5%. And then repeatability and hysteresis, I don't remember what it is. They tend to give it in terms of either millivolts or they'll give you the gain 2 and tell you the angle. So someone tell me why I might want to use say, for the sake of argument, we just love analog stuff, and we'll talk about this later, but I want analog everything. Why would I choose a Hall effect over a potentiometer? Yeah, okay, friction, what else? Yeah, true. Anything else? More general, why don't we have friction in a Hall effect sensor? There's no contact. So you're correct. We have no friction for the Hall effect sensor, but a more important thing is there's no contact. So there are fewer issues in terms of if you don't align potentiometers correctly with what's spinning them, you're going to apply a weird torque and rip it in half. Well, you might get a weird signal on a Hall effect, but you're not going to rip anything in half because it's not touching anything, right? So you still want to align it correctly, but even if you don't align it correctly, it's not going to mechanically break. The other issue is potentiometers, unless you have really sort of special ones, they're limited rotation. Not only are they limited rotation, they're very small rotation typically. And that's a pain in the butt a lot of times. And depending on the cheapness of the one you got, they're extremely high friction. Now again, these are general rules. These are not, I have seen and played with the ones that are both low friction and very high rotation. Typically, if you want a high rotation, they're called multi-turn pots, and they're more expensive. And so I used some for a project that gave me 10 turns. I think the little fidgets one is pretty standard. It's like 180 degrees or 170. And the multi-turn pots tend to be lower friction. And you can also get ones that, much like the slipper ring, it's just a disc with some type of annular resistive material and a little spring-loaded wiper. And so you can get continuous rotation on that. Okay, so let's talk about, so that's analog. And then there's digital. So the most standard digital type of encoder is called the incremental encoder. Let me start erasing some stuff. So, incremental. And then of the various types, we're going to be talking about optical encoders. So optical encoders basically work by shining a light on a little wheel. So, sorry, there's lots of measuring or camera work today. Okay, so see this little wheel in the center? That is an optical encoder code wheel. So to show you on the side, this plastic is razor thin. The middle silver part is aluminum, and that's called the hub. What's the central hole called? The bore. Okay. Now how do we hold it on the shaft? Any ideas? Set screw. Okay, good. So now, do you see how part of the wheel is clear and part of it's not? On the very out, it's not. And you see how there are multiple rings around it? So I don't think, we get blurry if I do that. So let me zoom in on the microscope and show you what those little slits look like. Okay. See those slits? They're really fine. This is, I don't know, this is 200 magnification right now. And you can still barely see them. And this is a really low resolution encoder in terms of encoders. So each one of those, basically, what this is black and clear, black and clear, black and clear. And what's happening, to draw it out on the board, is you shine a light, make it look like that, okay? And then don't think about it in terms of little strips. Think about it in terms of a hole. And then this is where the light goes, okay? So if we have direct line of sight, we go through the little slit and we see it. Now, if we were to draw the exact same thing here, it would reflect off and we would be blind. So this is on top of the black. This is on top of the black strip. The light can't go through the little black slit, and then this is on top of the clear slits where you actually can go through. So basically, we assign this a Boolean value of 1, and we assign this a Boolean value of 0. So now you see why it is digital. Okay, great. So basically, we've got a wheel. We're going to spin it. We have all these slits around it. And we're going to put our sensor right here sitting above it. And so what's the waveform going to look like? High-low, square wave. So this will probably be around 0 and probably be around 5 depending on the encoder. Okay, so does this look any different clockwise versus counterclockwise? No, it doesn't. Everyone see that? Square wave, forward and back look exactly the same. So this is an issue because we can't tell which direction the shaft is turning. So what we do is we use two sensors. And we put them 90 degrees out of phase. So what we want to do is we want to do this, where these are 90 degrees out of phase. So let's zoom in on one of these little black slits. Can everyone still see over here, or is this blinding everyone? So if this is one of the little black slits, so we put one sensor on top looking directly at the black slit, then we put another looking 90 degrees off in terms of 90 degrees phase shift from this. And so what that does is let's look at these permutations. So we've got 1, 1, then 0, 1, 0, 0, then 1, 0. So now, say we're moving this way, we would see 1, 1, 0, 1, 0, 0, 1, 0. And then if we look in reverse, you can see, let's zoom in at 0, 0. Say at some given time we have stopped spinning, we're stationary, and our sensors happen to be looking right at this spot on the code wheel, and we see 0, 0. If the next signal we see is a 1, 0, that tells us we went that way, versus we saw 0, 1, in which case it means we went that way. Does everyone see that? Typically these channels are called A and G. Okay. I thought that was hilarious. They're A and B, as they should be. Sorry. I could give a one-man open mic and just laugh uproariously. So yeah, the two channels are called A and B, and as you can see, if we go that way we see 1, 0, and if we go that way we see 0, 1, and clearly we can detect counterclockwise from clockwise rotation. What else does this give us? Yeah, it gives us speed. So for a given amount of time, we can count up the number of ticks we had. Anything else? Having two channels versus one? Increased resolution times 4. This type of thing where we have two sensors, A and B, is called a quadrature encoder. This is like the gold standard. Everyone uses this. And so what this is if you take the number of slits on here, that's called the CPR. And no, that is not the cardiopulmonary resuscitation. It's the counts per revolution. Basically the number of little black slits that we have. Counts per revolution. And the quadrature encoder means our resolution is CPR times 4.
Just be real careful with this. Different manufacturers will use something called PPR, and different manufacturers will do opposite definition of PPR and CPR, so you can be very specific when you call what they're referring to and whether or not you're going to get 4 times that number or exactly that number.
Rob is, I'm not sure the microphone can pick up Rob, so I will repeat what he said. There's something called PPR, which is pulses per revolution, and CPR, counts per revolution. Sometimes they are the exact same thing in terms of functional definitions. Sometimes they're opposite. What I have found is that companies who are selling crappy encoders at a very low resolution intentionally use this sort of mismatch of imprecise language to make it seem like, oh no, this is before the ×4. You get ×4 of this when in fact you don't, and you're expecting 4 times the resolution that you don't get. Yes?
Does it make a difference when you're selecting like decoder chips? I mean, it's still going to work the same if it's pulses per revolution or counts per revolution.
Decoder chips. Can you tell me what you mean by decoder chip?
Like if you want to say turn those into like counts, like 0 to like a really large number of counts. Like does it matter like what encoder you add?
No. Well, let me back up. Let's save that actually. Let's save that topic. We'll talk about how we read these in a sec. So basically, the way that this is, anyone want to hazard what the numerator would be for this if I were going to give you a resolution? So 2 pi radians over CPR times 4. Or alternatively, it could be 360 degrees. So now, basically, in our code or our decoder chip, as Alice just proposed, we're going to have to tell it what our resolution is. And so yes, it does matter what we're using, because if we get it wrong and tell the board or the code the wrong thing, then it won't be spinning properly.
So a quadrature encoder has resolution that's 4 times its counts per revolution.
Yes. So where do you get encoders? Well, there are lots of places. I tend to get mine from usdigital.com. They're really terrific. They're cheap. They're easy to use, and the people there are really, really nice. Actually, they're a sponsor of this course. And they always talk in terms of CPR, and it means the number of slits on it, and then it's just CPR times 4. And so they sell their base, like the worst resolution is 360 counts. Then I think they go up to 2500. And then if you want to get really fancy, you can get, Rob, you use Canon laser encoders, right?
There's a step in between the really high-end range power.
Uh-huh.
About $100, you can get 10,000 counts per revolution.
Okay, so 10,000.
And then if you want to spend $2,000, you can get 50 to 81,000 counts per revolution times 4. Those are Canon.
Yeah, so before the quadrature, 50 to 80K, that's a lot of counts. And we'll talk later about whether or not you can actually read that. Yep.
For those really high-end encoders, do you start worrying about like how long those signals are up in terms of like setup and hold times and all that other processes?
You definitely do worry, can I read the damn signal? Yes. And we'll get to that. So let's talk about how one might actually put on one of these encoders. Yeah.
The ones that actually come with certain motors, like if you buy them, do they tell you which manufacturer they're from?
May or may not. Probably not. Hopefully, anyone worth their salt who's selling you a part has stamped somewhere on there the part number for that part for exactly that reason. But I bought some high-end microscope slides secondhand, and I called the manufacturer and got every single data sheet and manufacturer number for every little subcomponent for that purpose.
So, like for example, you buy a Maxim motor, and sometimes you order with an encoder.
Uh-huh.
Do you usually do that, or do you like?
I usually don't.
Put on your own encoder?
I usually put on my own encoder, and I'm about to show you that. Rob, can you help me with this camera, please? And can you look up at the screen? Okay. So I'm going to show you a bunch of stuff. I don't know at this point if you all end up mounting an encoder yourselves this quarter or not. It remains to be determined. Hopefully you will have the pleasure / not pleasure of doing that. Okay? Okay. Now you need to come out a little bit. So let's just look at this for a sec. So this is a chunk of wood. It's a chunk of wood with a motor on it. This black thing is the motor. This is a little cable cap stand. Can you see the threads on it? Okay. And then this thing inside, anyone know what that is? Yeah, that's a coupler, or flexible shaft coupler, and we'll talk about that a little bit later. Now let's look at the back end here. This is the encoder. And so your encoders always come with a case on them. Anyone know why? Because otherwise they'll get gunk. And a little bit of gunk goes a long way towards killing your encoder. And when encoders get gunky, it's actually sometimes extremely difficult to debug them. So we got a case. I took the screws out, but fine. Okay, so let's take that off. And let's zoom in on the code wheel. See that code wheel? This is the, oh God. Beyond the point of return. Okay, so that's the code wheel. We're still a little blurry. Let's switch back to automatic. Okay, we're good. So that, no, oh God. All right, so that's the code wheel. That's the code wheel, and then what is this called? There are a lot of different terms. Sometimes it's called the code head or the read head or the sensor head. But basically this is what has that pair of light emitters and detectors. And then coming off of it, we have a bunch of pins here. Okay. Now let's take off a little bit more. So remember we said that this is a set screw? Can we go back to automatic?
It is.
Okay. So this is, typically they'll give you a little special Allen key. So you turn that, and now we're able to move this code wheel back and forth. See that? Now I can't take it off because this read head, can you see that read head is actually a slit? See that black slit there that the code wheel's in? So we have to take that off first. So let's take that off first. So US Digital ones are nice. They're just 2 screws. So I undo the screws. So installing the encoder is actually really simple, but if you're not careful, you can scratch up the code wheel and then you're done. Okay. So I took off the read head, I undid the set screw, and now I can take this off. Awesome. What do you think is the name for this shaft here? I'll give you a hint. It's on the back of the motor. It's the back shaft. Okay. Now, can anyone see there's a material in between this motor and this bolt plate here? See that? What does that material look like? Plywood. So this is a custom adapter between the encoder bolt plate and the bolt pattern on this motor. So you see these screws here? Right here? Those are the screws that are holding the bolt plate of the encoder to the adapter. And then let me get my Allen keys out. And
How are you attaching the adapter to the motor?
An excellent question. Okay. Okay. So I'm going to undo these screws.
So you can buy a motor with encoder and without, right?
Mm-hmm.
Why would you buy one? Like,
maybe they don't offer the resolution you want.
Which Maxon usually does now.
Yeah. Okay, so this is called the bolt plate of the encoder. And I'm not sure if you can tell, but it had, yeah, see those screws? So those screws go to these 3 holes here. Now notice there are also screws here. Those screws go into the back, let's back up, they go to the back of the motor. They are not the same pattern. So say you want a Maxon motor, because Maxon motors are really nice and they do exactly what you need in terms of torque and no cogging. But they don't sell an encoder of sufficient resolution. Fine, so you buy another encoder. Well, the chances of the bolt pattern on the random encoder and the motor lining up are basically 0. So you make this little adapter plate. So we have this sort of a strange bolt pattern with 4 screws for the adapter plate, and then this other bolt pattern with 3 screws for the encoder plate. Now, someone tell me something obvious about this picture other than the holes. there are two little wedges cut out here, here and here. So motors always have motor leads. They have to go somewhere. When you first buy them, they're typically sticking straight up, kind of like this back shaft. And if you just put, say the encoder plate did fit perfectly with the bolt pattern of the motor, you're still going to be smushing the motor leads. So that's why these are bent down still a little bit. See how I can bend them up and down? And if you do it more than about 3 times, they break? It's because I need to be able to bolt the encoder plate to the back of this adapter without smushing the motor leads. So that's another reason why you might use an adapter plate. Now, US Digital sells 2 types.
Good question. If the motor leads do the motor, is there any way to put it back?
No. You are screwed. You might be able to open up and resolder, but by that point I think you're screwed. When soldering onto a motor is, depending on the niceness of the motor, is hair raising, because you got 3 tries and then it fractures. Okay, let's zoom in a little bit more. How do you think that this different type of bolt plate attaches? The tape. I pull the tape off, it's double stick tape, and I smush it onto the back of the motor and I'm done. This is terrible. Please, for the love of God, don't ever do this. They should not be sold. It's kind of like cigarettes. It's a free country, and you're free to kill yourself if you want, but it's just stupid. So the advantage is, if I wanted to put this on some random motor with a bolt plate and I didn't want to have to get an adapter machined, it doesn't matter, right? I can just stick it on, and it doesn't matter what happens in terms of the screw holes. The disadvantage is eventually that glue is going to come off, and we always have a nice plethora of examples of crappy things students have built in our lab and then left. Let's zoom in on this. Okay. Let's zoom in on that back encoder. Now, does that look like that encoder is happy? Notice it's not concentric. There's a gap. It's sort of half hanging off. It's half hanging off because half the glue has come off and half of it hasn't. So watch this. Encoder on or off. Encoder on. Encoder off. Encoder on. Adhesive-backed encoder plates come off. Okay, fine. So it comes off, no problem. I'm going to take it off and put another double stick tape on it. Or maybe I learned my lesson and I'm not going to put double stick tape on it. The issue is that tape got in your screw holes and it hardened. And now you can't even bolt to the screws on it. You are fucked. We have a collection of about 10 different motors that students over the ages have decided they were too lazy to cut adapter plates. So they used the adhesive backed. It came off. Then they decided they had no recourse except to use screws, but the adhesive had gotten into the mounting holes for screws, had hardened, and you can't get it back out. And typically, even for like a really big honking 50 millimeter diameter Maxon motor, they're using either M2 or M1.6 screws, and retapping or cleaning out the threads, it's just not going to happen. You're going to break your tap. So never, ever in a billion years use adhesive-backed encoder plates, please. Yes?
If screws do thread, is there any way of getting it out?
Not really. I mean, there are these things that are basically a reverse drill bit that you can use for larger screws, but my percentage success in terms of getting stripped screws or stuck screws out of material is about 10%. And I'm pretty good at it. So, I mean, and especially for a small screw, there's just no chance. You're just done. Once you break a screw in something hard, it's not going to happen. Now, sometimes if you have access to the backside, you could use a special type of drill bit and just drill it out, but it's in a motor, right? So if you're machining the backside of your motor, the motor's dead. Much the same as fatiguing off the little motor leads. Okay, one last thing with this camera. Remember how I told you you cannot locate anything with screws? What did you see that was locating that motor? Did you see anything special? Were there any dowels or anything? I didn't see any dowels. Those are screw holes. They were all screw holes. So here's our motor, and here's our bolt plate. Okay, there are no dowel holes in here. So the only way, but look how I have a nice circle here in the middle, and I have this here shaft, this back shaft. Okay, then I have this little widget. Oh, my widget is blurry. Okay, so this is called a sintering tool. And this is a must-have, and they come for at least with US Digital, they come for every size. So what you do is you put the bolt plate on here, and I'm free to slide around whenever. But then when I stick my sintering tool in here, it's a very nice tight slip fit with the shaft, and then that conical section basically pushes down until we've located the central hole of the bolt plate and the back shaft of the motor. And now once I have this centered, then I put in the screws and I tighten it down. Can everyone see? And I'm going to draw this now too. So let me draw it. I'm saying this not only so you know how to install Encoder, but also so you understand the rules of screws not being used for locating purposes have not changed. They are the same. Okay, so what's happening is this is our plate and it has a central hole. Okay, and off somewhere yonder we have screw holes that we should never use for locating. And this is the back shaft, and we want to get these two concentric, because otherwise, what happens if you don't install an encoder with precise concentricity is you start skipping counts. So what happens is this sintering tool. This is a very precise fit. So we basically jam this cone section down until it's the same diameter to touch the edge, and then we're precisely located. And then and only then do we tighten the screws over here to locate or to bolt it. So we locate with the sintering tool, apply enough pressure with our thumb so it doesn't move, then we bolt down the screw holes. Yep?
So then the screws can be loose, right?
Yeah, screws can come loose.
So with that.
There are two things you can do for screws coming loose. You can either use lock washers or Loctite. We'll talk about that another day. Basically, you want to put a spring in there.
Why did you say that you can't use screw holes for locating?
Because screws are not precise. I mean, a 3 millimeter, an M3 or 3 millimeter screw might be anywhere from 2.7 to 3.1 millimeters. That's not precise enough to locate. Screws are only for bolting, and the only things for locating are very precise dowel pins. Let me show you a few other encoders, and these ones I can show on my own. So that is an encoder where it fits on the back shaft, right? And that was bolted on. Now here's another type. This is a pretty high-end encoder, and everyone see the kind of springy metal here? See that? So what this is it allows you to bolt it, and it takes away any need for that sintering tool. Any type of axial misalignment can be handled by this. Now it'll add friction, but it can handle it. But that's basically the same type of encoder, just with a different mounting option. So it can withstand different degrees of basically not centered. Now this is an encoder with its own shaft. So I can rotate that shaft, and there's a ball bearing. These two, at least from US Digital, come in two flavors: either ball bearing supported, which are the nice ones, or sleeve bearing, which is just sliding. And so I don't know. Let's come up with some good reasons why we might want to use this. Anything?
Put it away from the motor.
Huh?
You can put it away from the motor with some transmission thing.
Yeah. So we could put it somewhere other than directly on the end of the motor.
You put it on the wheels.
Yeah. Well, so basically, it's anywhere where maybe you don't want to put it directly on the end of a motor. What if your motor doesn't have a back shaft? A lot of motors don't have back shafts. The cheaper the motor, the less likely it is it has a back shaft. So maybe we're going to put this somewhere else. Now we can still put an encoder on the front shaft of a motor, but It's often inconvenient to do so, so maybe we'll belt this somewhere else. Maybe we don't want to actually actuate something. Maybe we only want to sense its position. So remember the Omni Bisensible, the haptic device at 6 degrees of freedom? It's only actuated in 3. It's sensed in all 6. So it makes a lot of sense to have an encoder on the back side of the shaft for the 3 actuated degrees, but not necessarily as much. There is no back shaft for the 3 that are passive. And then finally, this is a CUI. CUI makes a lot of encoders. I personally find them to be a pain in the butt. This is a real tiny encoder, and basically when you look at buying an encoder, you need to look at what the waveform is going to be when it comes out and what type of electrical requirements it has, because US Digital is nice. You just give it ground 5 volts and you read off A and B, but CUI is not. And I'm not going to go into the electrical architecture, but it's just really annoying to deal with. Okay, so this is an incremental encoder. We're able to count with quadrature. We're able to count forward and back, and now we know how to assemble it. Oh, there's one last tool. You know how we use shims? We have shims for the optical encoder. So let's look at this. Okay, see the code wheel? See how I can put it anywhere along there? How do I set the axial position of it? Let's look at this again. See how I can move it in? It's right here, and now I can move it in further. I have to know where to tighten it. So basically what it is, it's just as simple as this. Just basically a little, paper clip type thing, but it's a precise diameter of wire. So you slip this between the bolt plate and the encoder hub like that. Now obviously it shouldn't be cocked to one side, it should be like that. But that's a shim that tells us how far. Now we just stick the encoder hub until it's against the shim and we tighten. Everyone see that?
Then you take that thing off.
Yeah, then you take it off. You can't leave it on. So installing encoders, it consists of assembling a bunch of different parts. Like you have to take the encoder bolt plate and bolt it. Well, first you take the adapter plate and bolt that to the motor. Then you bolt the encoder base plate to the adapter plate. Then you put the code wheel on with the little shim. Then you tighten the set screw. Then you install the code wheel reader. Then you install the cover. And somewhere in there, when you're putting on the bolt plate, you have to use the sintering tool. It's a pain in the butt. But, as long as you follow the rules, you'll be just fine. Any questions about what we've said thus far?
Yeah, one quick one. So does it actually matter where the encoder is axially between the
Yes.
code?
It does very much. And it's manufacturer specific. So the reason they give you a shim is because if you don't use the shim, it probably won't work. So if this is the read head, and then it's passing light down in 2 sensors, the code wheel, you're asking basically how far does it have to be, right? The answer is it has to be really precise. That's why you use a shim. If we put it all, if we take it too close to either side, it's going to wobble and rub. That's bad. But if you actually zoomed in, and I'm not going to hear, it's not even centered, like between the gap. And they spec how far off you can be before it starts affecting your readings. So I'm giving you the general overview. When you go to install your first encoder, you're going to want to actually give a very careful read of the data sheet for the encoder to make sure, A, it does what you want, B, you have the drive electronics for it, and C, you know how to install it. Because any mistakes in any of those 3 areas will result in you not having a working encoder. Okay, so
Can you calibrate the encoder? Can you debug it?
there's no reason to. So you're asking, can you have an encoder that does weird stuff but then calibrated it out?
No, I'm just verifying that you have it installed correctly. I guess you count the number of revolutions and then you see the number of bits. Is that
Yeah. Most of the time encoders install just fine and you don't have any issues. what'll happen is what you're saying. You'll put it in a robot and you'll tell it to go 90 degrees and it'll look like 30, and you'll be like, hey, that's weird. So the first thing you check is your code. That's where you most often make the mistake because you screwed up the CPR. Maybe the count's wrong. Then you'll look to see if you have any noise on your line. You'll put it on an oscilloscope and check to see if you had any noise. If the oscilloscope looks clean, then you start to say, is there dirt in there, or maybe it's not concentric. And so you just kind of one by one.
What does quadrature mounting look like then?
That was a quadrature encoder I showed you. Yeah. I haven't seen non-quadrature encoders ever.
Okay. Oh, it's incorporated in the, you have like two.
Yeah, it's incorporated in the read head. To you, it's a black box. It's just code wheel, sensor, and you're done. I've never seen a non-quadrature encoder because there's just no reason not to do quadrature.
How much does that one cost?
Huh?
How much does that one cost?
US Digital goes anywhere from $30 to 80. 80 for the really, really high-end ones. They're pretty reasonable. So I called these, what type of encoders? Incremental. So, say, going back, do I still have theta up here? Okay, great. I have theta up here. How do I know when I boot up my robot where my arm started? Remember, it's incremental. All it tells me is based on where I was last time, did I go +1 to the right or -1 to the left? It doesn't tell me anything about where 0 is. They're incremental, and they have no way of figuring out where they started originally when the robot first booted up. But it really matters in my robot arm that this be, say this is 0 and this is 90, and if I calibrated this as 0, then I'd be trying to go into my own bicep for 90. So my robot has to know absolutely where my angle is, but my encoder isn't able to give me that because it's just incremental. So herein is the difference between an incremental encoder and an absolute encoder. Incremental doesn't have a 0. It just starts counting up or down from wherever it happens to start counting from. If I turn on power here, it starts counting here. If I turn on power here, it looks the exact same to that encoder. An absolute encoder knows in three-dimensional space that this is different from this, even if the incremental encoder can't tell. So there's an extra thing on the incremental encoder sometimes that you can use. If this is our code wheel, and these are all of our little slits, and A and B are looking at this, we'll have another ring, and that will have just one slit. Now sometimes they do something slightly different. It'll be a series of slits, but look for the annular pattern that is almost non-existent. That is called the index. And if you're looking at an encoder spec sheet, it might be called simply I. Sometimes they'll call it Z, just for fun, just to confuse you. So for just one revolution, this tells us where we are, right? It only happens once. It's a unique signal. So depending on how we bolted our code wheel to our motor, within one revolution of the motor, we know precisely where to 0. So what happens is for one revolution of a motor, which this would be great here, right? It's less than one revolution. What I'll do is I'll say when I wake up, say I'm at my joint limit, I just say go this way, and then I just say go that way until you see the index. Okay, I saw my index. Now you tell your encoder, hey, you're at 0. Now you start counting up or down. That's called homing the robot. If you don't home your robots don't work. And you can use the index on your encoder if you're only doing less than one revolution. Now I'm going to talk about another day. There's something else you need beyond the index so that your robot doesn't kill itself, but we're going to save that for another day. Okay.
One revolution of the output, right?
Of the shaft that the encoder's on. So if this encoder...
Presumably your arm is geared down, right? So you're
presumably, yep. So that's a good point. Say I have a gear head on here, so it's 1,000 revolutions on my on my motor shaft to get this motion. Does the index help us? No, because even though I want to go to this angle, maybe I just did 10,000 revolutions on the encoder to get there. So I just saw 10,000 indices. So the index will screw you if you use this before a gear head trying to get some 3D location on your joint. Because if we see, basically, this has to be unique. If we see more than one of this, then we don't know which revolution we saw. Potentiometer and Hall effect. Yes?
How do you ensure that you see the index if you have less than 360 degrees of, or less than one revolution?
Excellent question. We'll come.
Do you just set it up like that physically?
You tell me. Can we come back to that in a sec?
Yeah.
What was the other question?
So usually, I mean, the back shaft is usually straight out of the motor, though.
Yep.
If there's a gear head, then where do you put the encoder?
You always want to put the encoder, okay, not always. For my purposes, I always put the encoder on the back shaft because it gives me high resolution. So if I get, say 2,500 counts per revolution, and I only have one revolution of the gear head versus 10,000 revolutions of the motor shaft before the gear head, I get much higher resolution of my encoder before the gear head. It's on the back shaft. Now the other issue, and I'm not going to go into it much here, is there's called basically when you're controlling something that's moving, you've got some type of mass spring damper or something. You want to keep, in controls terminology, the relative order 2 or below. When you start putting encoders way away from the actual actuator, so say we went from a motor to a gear to a belt to a cable, and then finally on the final axis we put the encoder, that would be a relative order of much higher than 2, which means we might go unstable. It's a lot harder to control. So from controls perspective, it's a lot easier to put the encoder right on the actuator, on the motor. It's just easier to keep stable. Yeah.
So when you have a gear head, do you achieve that equation for counts per
Yeah. So basically, when you have a gear head, the in goes in here somewhere depending on which direction you're looking at it from. And you need to know if you're working in ineffective coordinates or joint coordinates. So if you're talking about one revolution of my, pitch roll, my roll pitch roll wrist, then one revolution here is a lot different from the 10 revolutions it took on my belt, right? Now let's go back to the index. So that's very interesting. And I guess I don't know.
Can you use two encoders to sort of like get over the fact that you're going through all these like belts and all the way?
One of the reasons why you use two encoders is because you want to measure compliance. If everything's stainless steel and it's really rigid, then there's no reason. But say you put a spring in between, and it's a really floppy spring, then you can measure the relative displacement between the two shafts, and then that gives you what? We got a spring, we just measured the deflection, so we got the force. So we can have force-controlled robots even though they're really position controlled. We'll get back to that. Let's talk about that index again. You're correct. Say this is the index, but we're only ever going to operate between, let's do real narrow, say here and here, and we bolt it down so that basically this point can move here and this point can move here, but that's it. And say our encoder read head is right here. Does everyone see? If the encoder read head represented by that is right here, and we can only ever go between these two dots, and the index is here, we'll never see the index. So the answer is, unfortunately, you need an O-scope or to have connected your encoder to the computer so you can see when you get the index, and you're going to have your Allen key ready, and you're going to try to put it wherever you need it to be, and then you bolt it down. This is imprecise. So it's not like in the real world you're here at 90 degrees and then you rotate your index until it's perfectly aligned and then you bolt it down. In reality, you kind of put it where you think it should be roughly. Then you have some way of measuring where you actually are. And then when your index gets there, you have a predefined zero offset. So I don't know, 49.239 degrees. instead of trying to shoot for something perfect, like say you want it at 45 degrees. You're never going to get it at 45 degrees ever. So just give up on that. If you have to have a number where when you start up, the robot says this is, I saw the index, this is the starting angle, and you can't get a perfect number, then you calibrate it to get whatever number it is. And it doesn't matter that it's a random number, it's repeatable. As long as that code wheel is set screw on, it's not shaken loose, every time you see the exact same starting angle. Everyone see that?
So it's a better way of doing it. Is
Yes.
adjusting to your.
The structure of our lecture has changed somewhat, so I will go ahead and change it more because some of you want to know more about this index. This is the difference between your robots working and not, by the way. And this is something that most people who start out in robotics have no clue about in terms of how to actually do it. So let's go a step further. Let me go back here for a sec. Potentiometers and Hall effect. Are those incremental or absolute? They're absolute. This is why we use them. So what you're going to see for one revolution is you're going to go from 0 to 5 volts usually. Now what's it look like when you do multiple turns? It's a sawtooth. Depending on how they do it. It usually wraps around. So we'll go 0 to 5, boom, back down to 0. To 5, boom, down 0 to 5. Now on the potentiometer it's not. Let me back. There's some. This is like the English language where there are more exceptions to the rules than there are rules themselves, which is why it's kind of frustrating. With the Hall effect, you definitely will see this characteristic sawtooth. With a potentiometer, you're actually not. You'll just see 0 to 5 because unless you have a special one where the wiper keeps going like a slip ring, but it's a limited rotation. So you're actually not going to keep turning. So even if you do 10 turns for a multi-turn pot, you're going to have a different slope, but you're only going to see one ramp. If you see that sawtooth, it's a Hall effect. So those are absolute. So now what you do is you want to pair an incremental with an absolute or an incremental with the index and a homing thing to make it absolute. What a lot of companies do is they don't want to screw with the index and the annoyance that we'll talk about in a second. They just want an incremental plus absolute. So you can either use a homing flag or you can use them in parallel. Something that Intuitive does is they actually want redundant encoders. So they'll have super nice incremental encoders and a homing flag so they know where they are precisely. Then they'll have a cheap little potentiometer somewhere in there, and if the two vary by too much, they shut the robot down because one of the sensors is dead. Redundant sensing. And it's very important to be able to withstand single point failures in medical robotics. So often you'll start out with something like an absolute encoder of a potentiometer plus an incremental with homing, and if they get mismatched, you shut down the robot for safety.
Why not just use an absolute encoder?
Why not use two absolute encoders? Because single point tolerance failure is bad. If your encoder goes out and you rip the guy's spleen out, then that's bad. So you need two encoders. The reason why you don't use two absolute encoders is because absolute encoders are ridiculously expensive, and they're also typically huge if they're really precise. So let me show you something. I've never seen absolute encoders used that aren't huge and aren't very expensive. Well, I still have not seen that though. Let's see. So, everyone see this? So basically, another form of an absolute encoder has different annuli or rings with different encoding. And so if you have one sensor per annulus, then you start to get a binary interpretation for each position. And one of the terms for it is gray encoding. But actually buying the gray encoders, unless US Digital does have one, typically they don't have the resolution. I mean, incremental encoders blow these out of the water in terms of resolution, typically in terms of the same price. So if you got $100 and you want the biggest, the best resolution for that $100, you're going to want to get incremental. Does everyone see this? How this is a unique pattern that doesn't happen for any other angle? That's really rare. Okay, so let's talk about.
One quick question.
Yeah.
So in practice, you absolute encoder, right? Your analog one doesn't need to be very precise because then you have a digital one that doesn't the revolution. Is that what it is? You just have to get into like within one revolution,
Yeah.
and then you use that one to sense it within one revolution, and then you really have like 3.
So remember when we talked about the potentiometer and the Hall effect, there were 2 main issues: linearity and repeatability. So would linearity matter if you were just trying to figure out, homing where you are? No, because you could figure out what that curve is, or you could have a lookup table. What really matters is repeatability in terms of homing. You want to know that every time you go to a certain spot, it will have a certain voltage. If it doesn't, you're screwed because you don't know where you are. Now, with my incremental encoder and my index, say, let's draw another picture. Okay, so this is my code wheel. Just assume that there are other little slits here. I don't want to draw a bunch of them. This is our index right here, and I'll call that I or Z. And then my sensor is here. Okay. I start up, I see the index, awesome. Will this ever happen? Probably not. So in actuality, you're going to start up and your index is going to be somewhere around there. Now say you didn't give yourself another absolute encoder. Which way should I turn to start looking, left or right? Well, you know because you can see this. Say you're the robot. Now, as the robot, from the robot's point of view, which way should you turn? You have no clue. You want to turn this way, but you have no way of knowing that. So what I do is I put basically an extra thing here. Everyone know what I mean by a slot sensor? You 218ers will. Okay. So this is a slot sensor. This is a slot. It's shining light through. When there's nothing there, it sees the light. When there is something there, it can't see the light. It returns a Boolean value of 0 or 1, which represents there's something here or there's not something here. That's a slot sensor. So let's put a slot sensor here. Let's put a slot sensor right up here. So we have the incremental encoder and we have the slot sensor. And now let's put a little flange here over only half of the workspace. Okay? So when I start up on this side, this appears what? There's nothing there. Say the index was on the other side here, and then this was over here. When it starts up, it will look different. So if I start up here and I see nothing in my slot sensor, I say turn that way. If I start up and I do see that I'm blocking the light, I know to turn the other way. Great. So why did we bother with the index to begin with? Does anyone know? I mean, this basically does what the index should, right?
Resolution.
Boom! This slot sensor that you buy is not nearly as accurate at locating that position as the index on your code wheel. All this is doing is telling us to turn clockwise or counterclockwise when we start up. Then, based on that, when we do find the index, it will be much more precisely and accurately located than we ever could have done with this.
Do you mount that onto the encoder?
No, I put this somewhere else. Wherever you've got space, basically.
I don't really see how this still solves our problem. So suppose our entire thing was like the other way around. So you were at the other end just before the shaded portion. So then it would probably go like 359 degrees to get to where it should.
You have to put, so I typically put that the transition from nothing to something smack dab in the middle of my workspace. And you have to guarantee that no matter where you are in your workspace, you know whether you're going to turn clockwise or counterclockwise. This doesn't work for multiple revolutions. So getting back to your question, this doesn't do any good if we put this on something that's spinning 10,000 times. This is only good for less than one revolution, right? Everyone see that? So if you did have an encoder and you want high resolution, you put it before your gearhead, but then this doesn't do anything for you, if you put this at the same place, you'd need to put this where you only have one revolution max. This is basically telling you, even for multiple revolutions, which revolution is it in that I need to start looking for that index. So if I am turning a wheel once and I'm getting 10,000 revolutions from the motor to do that, it tells the motor, okay, we're in the right revolution. You should start looking for the index. If you see the index here, that's the right one. Because remember, we're going to see 10,000 indices with a gearhead, and we need to know which one it is. So this can,
Do you use one of those infrared coin type sensors for that slot? Or
Yes, but not reflective. I use the slot type so that it gets rid of ambient light. Any questions about this? This is pretty key because otherwise it's just a pain to figure out where your robot is. This is one of these copy and paste type things. Once you've done it once, you're going to start doing it on all your joints because, okay, let's go back to another way of doing this. 3D accelerometer. That tells you where you are, right? If you start up your robot and no one's touching it, then it knows where gravity is, and assuming that your robot is right side up, then it knows where, through inverse kinematics, it knows where all of its joints are. So that's what I did on the spherical haptic device, especially with a friction differential, because the friction wheels can slip. Okay, well once they slip, you're kind of screwed, because if you're measuring the encoders, you don't know where the output is anymore. 3D accelerometer on the output doesn't care where the incremental encoders are. It will boot up and say, all right, I'm at 45 degrees, not only in this plane, but it'll give you all the planes, and then from that you back calculate what your joints must be at to have that angle, and then you're good. The only issue is, if you're doing this to your robot when it starts up, it's not going to work. So it's sort of a trade-off. And again, I might do something where I have a couple different, if it was a safety issue, I would have incremental encoders plus a 3D accelerometer plus a couple cheap potentiometers.
So like if you had an encoder on motor and then you also had an accelerometer and you're putting it on like a driving robot, you could potentially do like really precise like dead reckoning and things like that, right?
Not in that case, no. Those are some different issues in terms of wheel slippage and stuff. So a friend of mine, Morgan Quigley, is working on a low-cost arm, and one of his ideas early on was to put accelerometers on all the joints, because when you start up, that tells you the configuration of the arm. The dead reckoning is a little different for a variety of issues. You have to be careful with accelerometers in terms of drift and integration errors.
So even if you shake the robot, right? I mean, you can just take the average of the accelerometer output, so it should be fine, right? Or you just wait until.
I mean, I wouldn't be comfortable doing that. No, I wouldn't take the average of it. Someone said something. No. That depends. Oh, yeah, let's get back to that. Excellent. So, this is what I use for the CIA to not be able to broadcast to the fillings in my teeth. Does anyone know what this is in the context of an optical encoder?
Shield.
This is shielding. Why do you have shielding?
So you reduce noise.
So you reduce noise so that Samir's 3D accelerometer will work. So, going back to this. So we talked about analog, those are potentiometers and Hall effect sensors, and then digital. It's going to be on YouTube. That was really unnecessary. Okay. This is the optical encoder. Now say we got the most ridiculous potentiometers in the world. They're compact, they're cheap, they're perfect linearity, zero hysteresis, they're absolute, we don't have to do the homing, we don't have to do indices, they're easy to install, perfect. Why would we not use a potentiometer? Possibly. This is an analog signal, this is a digital signal. So now comes the discussion in terms of, okay, well, we have to interface with a computer at some point, and therein lies many nasties. Because the types of, and again, I apologize, we're going to get back to motors on Wednesday, but I have to start talking about this. There are the following types of signals that you're going to read. AI is what? Not artificial intelligence. Analog in. AO is what? Analog out. What is DI? Digital in. And what is DO? Digital out. Okay. And then I'm going to throw in some more, which is PWM out. And then counters. And this is parentheses in. You use a counter for your encoders. So, this gives you, on that potentiometer, say it's at 3.99999 volts, you will see that on your computer. Analog out takes a number and turns it into a voltage on your robot. Digital in was at a 0 or 1. Digital out sets it to 0 or 1. PWM out, I will explain another time. And counters in basically says how many times have we seen that tick on the encoder, including quadrature. So real quick, analog. We have noise problems, and we have resolution problems. Digital. We have communications problems. We have quantization problems. And we have resolution problems. Now, we don't have time to get to all of these. But the reason I wore my hat is because if you have a potentiometer, even if you have a really nice way of reading it into the computer, you may have noise issues where even a perfect sine wave looks nasty and sawtooth. And there are different things you can do about it, but sometimes you can't do much about it. You can mitigate it, but not eliminate it. And so there's a trade-off between, do I want an analog sensor or a digital sensor? And that's in terms of, how do I want to read it into the computer? What resolution do I need? What's the ambient noise? And what frequencies am I reading at? We're going to have to get to all of those another day. But just one last thing. And we'll need the... Okay, so this is the cable. Okay, can everyone see this? These are the wires going into my encoder. Everyone see the greenish yellowish one all the way on the right? See the one directly to its left? You can't tell here, that is not a normal electrical wire. That is a glorified piece of aluminum foil. That's a shield. All good encoder lines, basically all sensor lines, have a hat of aluminum foil that they wear called shielding. And so what happens is electrical noise, be it inductive, capacitive, etc., it's going to get passed on to this, and then when I hook this hat up to ground, my noise, most of it goes away. And so that's why there's an extra line on my encoder which is dedicated just for shielding, and I hook it to ground and most of my noise goes away. But this, and I'm going to keep this hat, and maybe one of you lucky people can wear it next week. This is a big reason why sometimes you want analog and sometimes you want digital. I think we're out of time. Office hours tonight, 7 to 9. Rob's doing them.
So it's not a shield that's wrapped around the wires?
It is wrapped around.
Oh, it is wrapped around the wires.
I couldn't figure out a creative way of